continue our discussion on CMOS circuits. Just to remind you, CMOS stands for complementary MOSFET circuits. In complementary MOSFET circuits, in CMOS, we have PMOS and NMOS simultaneously present on the chip. These are very widely used circuit, and the most advanced circuits are actually CMOS circuits, and there are two basic reasons for their popularity. One is that the power consumption is extremely low in CMOS circuits. This we will show that why the power dissipation, the power consumption is very small. It is in fact the lowest of all the known logics. And another reason is that switching is very fast. Then on the previous turn we said that as an example of CMOS circuit we take a inverter circuit, which is also called a NOT circuit, and a inverter circuit is when input it has only one input and one output. So, when the input is high, the output is low, and when input is low, the output is high. That means the input voltage is inverted. That is why it is called inverter. Now, this was also said that why we are taking the inverter, because inverter is basic for the digital electronics. The universal gates, NOR gate and NAND gate, these can be realized by the extension of inverter circuit. So, what is the CMOS inverter? The circuit is this. This is PMOS, PMOSFETs, and this is NMOS, NMOSFET, and this is the DC supply VDD. The input is obtained by connecting gates together for both the MOSFETs, and the output is taken by connecting both the drains, drain of PMOS and drain of NMOS. They are connected together, and from there the V out is taken. Now, we also discussed that actually PMOS requires a negative supply voltage that can be provided by giving a positive source voltage. So, that is the way these NMOSFET and PMOSFETs are connected. So, this source is connected to this supply plus terminal, and this way we can get bias both the MOSFETs by a single supply. Then we obtained two equations, one for the input voltage is what is the voltage here, and that is we can write actually the two equations which we got earlier. This was Vi, this is equal to VGSN, N stands for NMOS. This is equal to V VDD minus VSG for P. This is equation 1. Input is equal to this voltage, which is VGSN, and that is also equal to VDD minus this voltage, that is VSGP. And similarly we can write for V out, this is VDSN, this is D, this is N, and this is S. So, DSN for NMOS, and which is equal to VDD minus VSD for P, and this we call equation 2. These two equations we obtained the other day, which are simple. These are simple, the expressions which you already see, that V out will be this voltage, which is this, and this is equal to this minus this. So, these two equations we will be using later also. Now, the two cases we can discuss, and the two cases are case 1 when input is low, that is Vi is low. So, this is 0 volt. Now, you can see, you will have to keep in mind this circuit. When this voltage is low, that means this NMOS will be off, because in this case VGSN is equal to Vi, which is 0, and so obviously it is less than the threshold voltage required for the NMOS, and hence therefore NMOS is in off state, is off, and when the transistor is off, obviously the drain current ID in the NMOS, so we write IDN, this is equal to 0. And then for PMOS, this is NMOS is off, this MOS is off. Now, let us find out when input is low, what about PMOS. So, for PMOS, from equation 1, we get, this is equation 1, from there we write VSGP, which will be equal to VDD minus VGSN. This is what we write. So, VSGP is equal to VDD minus VGSN, and VGSN is Vi. So, this is equal to VDD minus Vi, and since Vi is 0, so this is simply VSGP, this is at the potential VDD, and this is greater than the threshold voltage because of the way it is connected. The way we have connected, the drain is here, the source is here. So, when VSGP is equal to VDD, it is greater than VT for P, and therefore, PMOS, this was one state, NMOS was off, and now therefore, PMOS is conducting. That means it is on. MOSFETs, they are in series. So, that will imply that drain current in the PMOS should be equal to the drain current in the NMOS, because both are in the series, and that implies that IDP is equal to 0. Now, it is conducting, but the drain current is 0, and if you look at the drain characteristics, this situation is just in the beginning of the ohmic linear region. So, it puts PMOS in the linear ohmic region where IDP ohmic is equal to 0. And once we write the expression, which when we talked about the enhancement MOSFET, then in ohmic region the drain current is given by a certain expression. So, that we use here. So, IDP ohmic is equal to K is the constant, the conductivity constant, and this is VSGP plus VT P. Here proper sign of VT has been used, and VSD for P minus VDS for P square by 2. This is the equation, and because VSG for P is equal to VDD here. Here this was 0, so this one VSGP is equal to VDD. This is what we have written. So, here we can replace this by VDD. So, IDP ohmic becomes equal to K VDD plus VT for P, VSD for P minus VDS P square by 2 and this is equal to 0 here. So, this we equate to 0. Then the solution of this equation with this 0, k is not 0 and other parameters are not 0, this will imply that it has the solution, it has the solution VSP SDP is 0. Now, substituting this in equation 2 here, VSDP is 0, that will tell us what will be the output in this equation. So, substituting VSDP equal to 0 in equation 2, we have V out equal to VDD, that is high. This is what we expect from the inverter. In the inverter, when the input is high, input is low, the case under consideration, then it results into high output, and this is what we are getting. So, this is case 1 that completes, and then we go for case 2 when input V I is high, meaning V I is V D D. We can see here also, once we say in the first case, then when input is low, so this was off and this was conducting. So, what is the voltage which you expect at output, because this is conducting and this is off. So, obviously V 0 has to be equal to V D D, and this is what we are getting. Similarly, in this case, when this is high, input is high, this will be conducting, and once this is conducting, very low impedance. So, then this output, once it is conducting, this will be very close to 0, and this is what we are going to have. So, under this condition, when V I is V D D, then and V D D is greater than V T. So, in this case NMOS will be on and it operates in the linear ohmic region. But PMOS, let us see, this is the state of the NMOS. NMOS is conducting. Then what about the PMOS? PMOS we will see is cut off. PMOS is off for V I equal to V D D, and this we can see from equation 1. See from equation 1, which was V S G P, this is equal to V D D minus V G S N, and G S N is V D D is V I, and V I is V D D. So, V S G P, this is V D D minus V D D, which is 0. Therefore, this is off, PMOS is off, but because of the fact that both are connected in series, IDN ohmic should be equal to IDP off, and this is equal to 0. And once we write the equation for the drain current for the NMOS, as we did in the previous case, here IDN, this is equal to K for N, that was for the P previous time when we did, and this is VGSN plus VTN VSDN minus VSDN square by 2. And since VGSN, that is equal to input, which is VDD. So, we replace this by VDD and we get IDN equal to Kn VDD plus VTN VSDN minus VSDN square by 2. This is equal to 0, and the solution of this equation is that VSDN is equal to 0. This has to be 0 only then, because other quantities are not 0. So, VSN is 0 and this is the same as VDSN. And what was output? You will remember that output V0 was VDSN and this is 0. So, output is low. This is the working of CMOS. When the input, this input is low, output is high, and when input is high, output is low. This is what we get here, and that is how a CMOS, the complementary MOS inverter, works. We said that dissipation in the CMOS is least. Let us discuss that point. Power dissipation and power consumption are one and the same thing in electronics. Power dissipation in CMOS, and why power consumed is equal to power dissipated, because in equilibrium whatever power the transistor is dissipating, that is the heat which is being generated by power consumed. If, for example, heat dissipation is less, then temperature will go on increasing and finally there will be a thermal runaway and the device will burn. So, always power consumption is same as power dissipation. So, now we consider that why power dissipation in CMOS is least. There are two ways the power, there are two types of dissipation. One is static power dissipation, and the other is dynamic power dissipation. Dynamic power dissipation. We take one by one. So, first we take static power dissipation. Static power dissipation occurs when these MOSFETs, they have changed states. They have changed states. For example, from high output to low output or the vice versa. So, the states have already changed. So, what is the power dissipation in that changed state, that is called static power dissipation. Now, we have seen that in when the state changes, for example, from low, when V out is low, in this case PMOS was off. And the drain current ID in the CMOS was 0, in fact, for the total drain current was 0 in the CMOS. And similarly, when it changes state the other way, then the drain current was still 0. In either case, this is off, this is on, but drain current is 0, or when this is off, this is on, still the drain current is 0. So, the static power dissipation PD, power dissipation we write normally as PD static, and this is drain current in the high output case. This was 0 as we know, and ID low output, in this case as well this was 0, and this is to be multiplied by VDD by 2. So, currents being 0, so PD static is 0, because the drain current, when the states have already changed, the drain currents are 0. But there are in practice leakage current of the order of 10 to power minus 18 amperes, very small current, they do exist. This is about static power dissipation. Now, the dynamic power dissipation. Dynamic power dissipation. We said above that when the MOSFETs have changed states, then the drain current is 0, and that gives the static dissipation to be 0. But dynamic power dissipation occurs when both these MOSFETs, they are changing states. During that transient period, when the states are being changed from on to off or from off to on, then for that short period the current, drain current flows in the CMOS, and that accounts for the dynamic power dissipation. I repeat that in the dynamic power dissipation, when MOSFETs are changing states from conducting to non-conducting and non-conducting to conducting, then during that small transient time there is a drain current, and that gives the dynamic power dissipation. And it can be shown that PD dynamic is equal to CL nu into VDD square, where CL is the load capacitance. At the output, what is the capacitance? All circuits have inherent capacitance associated with them. So, the CL is the load capacitance and nu is the switching frequency. switching frequency. And so, this is the dynamic loss, and this is actually of the order of few tens of PD dynamic. This is of the order of few tens of microwatts, very small. So, the static dissipation is close to 0 and dynamic dissipation is of the order of few tens of microwatts per circuit, per inverter for example, and that if we combine the two, the total power dissipation is extremely low, and this is the logic. This is I am repeating the statement that CMOS logic demonstrates least power losses. Now, this is about this module on MOSFETs and FETs. Let us take few numerical examples and then I will summarize what we have done in this unit. As a first example, let us take problem 1. For an N junction field effect transistor, the device parameters are the source drain short circuited current is the highest current in the N junction field effect transistor IDSS. This is 10 milliampere for the device, and Vp, the punch through voltage, is minus 4 volts. You remember the structure of junction field. There is a drain, there is a source, and the channel is implanted, and when the gate is shorted to the source, then the drain current is the maximum, and when we operate this with the smaller voltages, more negative voltages, then drain current falls. So, in this N junction field effect transistor, the IDSS is 10 milliampere and punch through voltage is 4 volts. Then we have to calculate the drain current ID for different voltages between gate and source. VGS equal to 0. This is A part. B part, VGS minus 2 volt, and then C, VGS is minus 4 volts. Under these three conditions, we have to find out the drain current when these are the parameters available. Now, we talk about the solution. Obviously, the device is working in the saturation region, where for JFET the drain current is given IDSS 1 minus VGS Vp square. This equation we are supposed to use. We have to find out ID for various gate source voltages, where IDSS is given as 10 milliampere, and let us first see part A when VGS is 0. So, this term is 0 and this is ID. In this case the drain current is equal to IDSS, which is given as 10 milliampere, and this is of course understood. It is well understood because the gate source voltage is 0 here. This is drain source and this is drain, and this is the channel. When the gate is shorted, VGS is made 0, that is the maximum current which flows in the device. So, this is this. Then when VGS B part, when VGS is minus 2 volts, in that case ID, again in the same expression we put the value of IDSS, that is 10 milliampere into 1 minus the voltage is minus 2 volts and this is minus 4 volts square, and so this is equal to 10 milliampere 1 minus 1 by 2 square, which gives this to be drain current is 2.5 milliampere. So, when the gate was shorted to source, the drain current was 10 milliamperes, and when it is given a voltage of minus 2, the drain current is reduced to 2.5 milliamps. And case 3, when VGS is equal to minus 4 volts, in this case in the same expression IDSS is 10 milliamperes, here 1 minus 4 by minus 4 square. So, this is 0, 1 by 1, 10 milliamperes 1 minus 1. So, this is 0, ID is 0. This is also understood actually, because for the device the pinch off voltage was 4 and this is that where the current reduces to 0. All these points you can see from the drain characteristics, that when gate source voltage is 0, maximum drain current for the N type JFET flows, and when this is made negative, VGS is made negative, current falls, and when VGS is made equal to VP, the magnitudes are same, then the drain current reduces to 0. So, this is the solution of the problem. Let us take another problem. This is problem 2. There is a circuit which makes use of PJFET, and the circuit is this. This is RD, this is RS, this is RG, and this is minus VDD because it is p type junction field effect transistor, and the current flows this way here. So, here what is available is that VDD is 12 volts, sign is provided here. So, it is actually minus 12 volts, the magnitude is 12 volts, and the drain current IDSS is 8 milliampere, and punch through is 4 volts, and ID is 4 milliampere, and the VDS, when the 4 milliampere current flows, VDS, this voltage here, this is equal to, I can show it here, VDS, this is equal to 8 volts. We have to find out the values of these two resistors. Find values of resistors RD and RS. This is the problem. Here this is the circuit, and this is a P JFET which has IDSS as 8 milliampere and VP as 4 volts. In the circuit, this battery is 12 volts, and the drain current of 4 milliamperes gives a voltage drop of 8 volts here. So, what is the value of these two resistors RS and RD, that we have to find out. So, the solution of this, we again use the same equation. The drain current is IDSS 1 minus VGS minus VP square, and it is given that ID is 4 milliamperes. So, 4 milliamperes, IDSS is 8 milliampere, 1 minus VGS minus VP is 4, and we can find out the value of, the only unknown is VGS. So, this milliampere is cancelled, and it is very simple calculation. From here we get VGS, this is equal to 3 volts, VGS, this is 3 volts, and you will remember that it is a self bias circuit. So, this 3 volts is to be provided by this resistor RS. So, once we know VGS is equal to 3 volts, then we can get RS resistor is equal to VGS, the magnitude of VGS by ID, that will give the value of resistance. So, this is 3 volts and ID is 4 milliamperes, that means minus 3 amperes. This gives RS equal to 750 ohms. We have found out the value of RS, and to find out the value of RD, this drain resistance, we have to apply we have to sum up the voltages in the output circuit. Here we sum up the voltages, and that will give KVL, Kirchhoff's voltage law, at output. When we apply, we get VDD equal to ID RS RD plus VDS. This is given 12. This is 4 ID is 4 milliamps. So, minus 3 amperes into 750 ohms plus RD plus this is 8 volts. We solve for RD and RD comes out to be 250 ohms. This is the way we can find out the values of the two resistors RS 750 ohms and RD as 250 ohms. Let us take one more example and let us take this, that a EMOS, this is problem 3rd, EMOSFET, the data sheet specifies VGS as 6 volts and ID on as 60 milliamperes, VT as 2 volts. Determine the drain current. Drain current we have to find out at VGS equal to 4 volts. So, this is one example we are taking a MOSFET. This is the data available on the data the manufacturers give with the data sheet, and this is what the problem is. Drain current is to be determined at VGS 4 volts. Now, the solution, this data we can use to find out the constant K, the conductivity constant, conductance constant of the device of the MOSFETs. This we discussed when we were talking about the MOSFETs, and this constant K, one of the ways we can get is through this data, and this was given to be ID on VGS minus VT square. So, we substitute the values. ID on is given as 60 milliampere and this is given 6 volts, this is 2 volts square and this gives 3.75 milliampere per volt square. This is the constant K, and then for the EMOS, the drain current K into VGS minus VT square. This was the expression that expresses the drain current in the saturation region. When we substitute the values, this is 3.75 in milliamperes, mind it, we are putting in milliamperes, and this 4 volts 2 volts square, then this comes out to be 15 milliampere. So, ID is equal to 15 milliampere. This is what we were supposed to determine. So, this was the problem on EMOSFET, and similarly it can be on DMOSFET, and such expressions can be used there too. Last example, another, this is on the amplifier, common source amplifier. Last and fourth problem, this is common source CS amplifier. The circuit is this. this is R1, R2, this is 800 K, this is 200 K kilo ohms, and this is RD, which is 4 K, and RD, and this is 250 ohms, and this is also bypassed, and the output is taken here. This is the load of 8 K, output is taken here, and this is plus VDD equal to 15 volts. So, here two things have to be determined. This is the circuit where all parameters are known, and we have to find out what is input impedance and voltage gain. First we draw this is the input V I, and output is taken here. First we have to draw the AC equivalent. For that, DC voltage sources have to be grounded, and these coupling capacitors C1 and C2 are of sufficiently large value, and they have to be taken as short at the frequency for which the amplifier is meant, and this is bypass capacitor C, that is also large, and this will be shorted. So, we can draw a simple equivalent AC circuit this is 8 K, this is 4 K, and this is all grounded. This is the equivalent circuit. This is R1, this is R2, this is 800 K, and this is 200 K. Now, first the input impedance. Input impedance we are seeing in the equivalent circuit that they are coming in parallel, and to this will come what is the impedance of the amplifier of the device itself, the input here. So, the input impedance of the amplifier is R1 in parallel to R2 in parallel with the Zi of the device. This is for the FET, which is very high, and remember that in parallel combination very high resistances can be neglected. So, this is actually Ri, simply R1 in parallel with R2, and this is 800 K parallel 200 K. So, this comes out to be 160 kilo ohms. This is the input impedance as we will measure here. And then gain. The GM was given for this actually, which I just forgot to write, that GM for the device is given 2.5 milliamperes per volt, and which is also written as millimos. So, part B, the gain AB, it is simply GM into RL, effective load. Effective load is the parallel combination of these two. So, hence RL in the present case is 4 K and 8 K, and that comes out to be 2.6 K. So, then AV becomes 2.5 into 10 to the power minus 3, that is the value of GM, and into 2.6 K. So, this is 6.5. The voltage gain for the common source amplifier is 6.5. So, these are the few typical examples which I took for the numerical problems. That finishes our this unit, and here what we have done, we started with the junction field effect transistor. We gave how it is constructed, what is the structure of junction field effect transistor, how does it work, what are its IV characteristics. Then we went for MOSFETs, and MOSFETs, the DMOSFET, depletion MOSFET and enhancement MOSFET. Depletion MOSFET can be used as in depletion mode as well as in enhancement mode. And enhancement mode, there is no channel existing in the beginning, but the applied voltage at the gate creates channel. And enhancement mode, then we developed a model for the transistor which is applicable for junction field effect transistors and for FETs. And also we analyzed the 3 amplifiers. Common source amplifier is most widely used, and common drain is like emitter follower, which is used for matching purposes. And then we took CMOS devices, and we indicated that CMOS gives the lowest losses, very high speed of switching, and most advanced circuits are made in CMOS. So, this is this module is all about.